Hi everyone! Today I'm going to show you a real example of how calculus, especially limit and derivative, is used in biology field. So now we're looking at the enzyme kinetic. An enzyme kinetic using a Michaelis-Menten equation. I will walk you through the each step in the simple way. So let's get started. The Michaelis-Menten equation is the mathematical model that describes the rate at which an enzyme categorizes a chemical reaction. It is based on the idea that enzymes work by binding to their substrate, which is the chemical that they are acting on, and then converting it into the product. As amount of the substrate decreases with the time, the amount of product also increases with the time. The formula of Michaelis-Menten equation in this is V equal V max times S divided by Km plus S, where V is the rate of the reaction as measured by the formatting of the product, and V max is the maximum velocity of the reaction, which is the rate of the reaction when the enzyme is fully saturated with the substrate, and S represents the concentration of substrate, and the last one Km is the Michaelis constant, which is measured by affinity of enzyme for the substrate. It is equal to the substrate concentration at which the enzyme is working at the half of its maximum velocity. So now we're gonna use the limit to application it first. First, let's take the limit at the substrate concentration go to 0 first. So limit S go to 0, V equal V max times S divided by Km plus S. And when the S is very small compared to Km, we can approximate into Km. So the equation becomes V equal V max divided by Km times S.
Okay, limit 2. When substrate concentration is extremely high, next let's take the limit at the substrate gone to infinity. Limits as S approaches infinity, V max times S divided by Km plus S. Okay, next when S is here, the Km becomes negligible, so K sub M plus S is approximately equal to S. The equation simplifies to as the substrate concentration increases, V of S approaches V max, meaning at very high substrate concentration the enzyme becomes saturated. Even if we add more substrate, the reaction rate stays close to V max. This is called zero-order behavior. Next, derivative sensitivity of the reaction rate. Now, let's differentiate the Michaelis-Menten function to see how sensitive the reaction rate is to change in substrate concentration. Derivative of V with respect to S equals V max multiplied by Km divided by Km plus S squared. This derivative tells us how much the reaction rate change when S increase slightly. Okay, next, biological meaning of the derivative. This part is very important in biology. When S equals 0, dV dy ds equals V max dy Km. This is the maximum sensitivity. Adding substrate increase the reaction speed more. And the next, as S increase, the denominator become larger. Open parenthesis Km plus S close parenthesis square. So derivatives get smaller. This means the enzyme becomes less sensitive. Adding more substrate give a smaller effect. This makes real biology when the enzyme is near saturation. Increasing substrate doesn't help much. Now let's plug in some numbers to make everything more visual. Example, we assume V max equal 100, Km equal 10, V equal 100 times 1 over 11, which equal 9.09. The derivative of V with respect to S is approximately 8.26. Case 2. V equal 100 times 10 over 20 is equal 50. The derivative of V with respect to s is equal to 2.5. Case 3. V equal 100 times 100 over 110 with equal 90.9. The derivative of V with respect to s is approximately 0.826. Reaction gets faster but sensitivity drops dramatically as the enzyme approaches saturation. And that's the full explanation of how limit and derivative help us understand enzyme kinetics. We use calculus to analyze low substance level, high substance level, and how sensitive the reaction is to change in S.